So I had made a mistake in the last class. Remember, I tried to do this integral, and basically my mistake was that here I wrote plus instead of minus, right? So the correct answer is minus, right? The integral will be minus. And in fact, I added this equation to the crib sheet now. So you can actually see the updated crib sheet. I named it crib sheet, I think 2021. So you can see the new crib sheet on Moodle. So basically, what we can do now is that we can just plug in. And this equation, these two equations are the same, right? What I did in the one in the box is that I multiplied both sides by a, right? Otherwise, they are the same thing. And I added the one in the box to the crib sheet because I think it's a bit, simpler than the other one. So this was the last slide in the previous class. So we wanted to calculate expected value of y given x, right? And this is why basically we need this equation. I have to calculate the integral of y times e to the ay, right? So this is exactly the equation in the previous slide that I just showed you. And since we know the integral, we simply plug in, right? So this is the first term, and this is the second term of the integral, right? And we write the bounds from 1500 to infinity. And it's just, doing the computation, really, nothing special, right? So you just plug in the bounds, and at the end you get 2000. So I do mention that there's nothing special, but, you should try to do these yourself by hand and then compare to the slides because, you just become more confident as you do them more and more, right? Otherwise, if you just look at the slides, yeah, they do make sense. But, if you do them yourself, you realize that they are actually not difficult. Any questions? So, like I said, you don't have to worry about this equation. I have added it to the crib sheet now. So in case, you need it, you can just use it. Okay. Now, the next concept that we introduce is the concept of independent random variable, right? So in fact, it's quite similar to what we saw before, right? So here we have the joint PDF, right? F of x and y. And if x and y are independent, then the joint PDF is the multiplication of the marginal over x over marginal over y, right? What we had before for sets is in fact quite similar to this equation. We had for sets, so if A and B are two sets, we had the probability of P of A and B, intersection B. So P of set A intersection set B is equal to P of A times P of B, right? If A and B independent, right? So this is quite similar. So the joint PDF should be the multiplication of the marginals, or f of y given x should be f of y, right? Again, this is quite similar. What we had before was P of A given B is P of A, for example, right? So this is also quite similar to what we had before for sets, right? The difference here is that now we are talking about PDFs, probability distribution functions, right? Or the other way around, P of x given y is P of x. Sorry, f of x given y is f of x. And finally, the fourth one says that for any set A and B, P of x and y, so here actually we could have written intersection, right? X in A and y in B is equal to P of x in A times P of y in B. So the fourth one is really, really hard to check Any ideas why it's proved this equation with the fourth one? Like it's hard to the point that it's probably useless, the fourth one. Like it's we can't really prove two PDFs are independent using the fourth property.
Could it be that it says any set
Yeah.
A and B? So that
Exactly.
check like all the sets possible.
Yeah, you're right, Mike. So it basically says that for any sets A and B, right? And we can't really check all the sets, right? There are so many sets that we can define. So because of that, it's really hard to prove independence with the fourth, with the fourth property. Usually, for the PDFs, the first one is the easiest one. Okay, so let's look at an example. So here we have a PDF that's exponential, right? So some coefficient times e to the minus ax minus by, right? So we have the PDF, and this is defined for positive x and positive y, right? Sorry, non-negative x and non-negative y. So we want to see whether x and y are independent, right? So we want to use the first property, whether f of x times f of y is equal to f of x and y, right? So what we do is that first we calculate the marginal probability of x, right? So here it's always a good idea to draw your region. So this function is defined for this region, for x and y positive, right? It's important because when you want to write this integral, you can't simply write 0 to infinity, right? You have to find these bounds from the range, from the region where the integral is defined, right? So in this case, the region is quite easy, right? So when I integrate with respect to y, my y changes from 0 to infinity, right? So my bounds are 0 to infinity. Right? So this is very important. Never, overlook the conditions, in front of the PDF, because the conditions actually tell you where the PDF is defined. They are very, very important. Right? So the rest, once we know the bounds, the rest is easy. We have to calculate this integral. When we do this integral, note that this part is a constant, right? Because anything that's not a function of y is a constant, comes out of the integral, right? So the integral is going to be this for f of x. So this is my f of x. And similarly for y, the range for the bounds of x is going to be, so x is going to change from 0 to infinity, right? And because of that, my bounds here are from 0 to infinity, right? D of x. So now the y part is a constant. So this part comes out of the integral, right? And we do the integral, and at the end we get this for f of y. Right? So the next step is that I have to multiply these two functions, right? So let's multiply them together. So f of x times f of y is going to be, so 0.001 and 0.002 multiplied by each other, they will give me 2e minus 6, right? Because there are 3 decimal points here and 3 decimal points here, so 3 plus 3 is 6. And then e to the minus 0.001x minus 0.002y, right? And then when we check this, right, with the original joint PDF, they are exactly the same thing, right? So in other words, f of x and y is equal to f of x times f of y. Yeah. Yeah, we have 2 to the 10 minus 6 here, and we have also here. Was that your question? Yeah, so it's the, yeah, so these are two different notations, you know, so isn't it 2e minus 6 is 2 times 10 to the minus 6? Right? Yeah, so, yeah, for e I didn't mean exponential function, yeah, thank you. Yeah. Okay, so since we proved that, you know, the product of the marginals is equal to the joint PDF, then x and y are independent, right? So the next part of the question wants the probability of x more than 1,000 and y less than 1,000, right? So basically, whenever a probability is needed, we have to draw the range, right? So the range is going to be, so if this is 1,000, and this is 1,000. So x has to be more and y less, right? So this is the range that we should integrate. Right? So one way would be to do it, you know, directly from the beginning. Say that, okay, I have my PDF, therefore P is equal to double integral of f of x and y. Here the range is easy, you know, it's a rectangle, so I can do like dx dy, the order doesn't matter. And for x, my range is from 1,000 to infinity, and the range for my y is from 0 to 1,000, right? So I can do this, but it's not a good idea, right? There is an easier solution because I just proved that, you know, this PDF is independent. Sorry, x and y are independent from each other, right? So instead of doing the integral for f of x and y, what I can do is that I can break this probability, right, into two probabilities because x and y are independent, right? So this is the interesting part, right? So remember, if x and y are independent, then probability of x in A and y in B is equal to P of x times P of y, right? So I use the fact that they are independent to simplify, you know, a joint probability into two, you know, simple one-dimensional probabilities, right? So now this is an easy problem because I have f of x and I also have f of y, right? So since I have f of x and I also have f of y, all I need to do is to integrate f of x and f of y and then multiply them by each other. Is there anybody who wants me to do actually these integrals? So it's not in the slides. So this integral is not written in the slide, but I will be happy to do it. Is there anybody who wants me to do this one or the other one? No? Okay, perfect. So, so the first integral is going to be this guy, e to the minus 1, and the second one is going to be the second term. And then we get the probability is 0.3. Okay.
I had a quick question.
Yeah.
So obviously for the minus 1 right there, you plug in the 1,000 into that formula above. But then what happens to the decimal in front of it, the 0.001?
Yeah, okay. So the decimal goes away because look at, so basically what we are doing is I'm doing the integral of a e to the ax, and this integral is going to be e to the ax, right?
Yeah, no, that makes sense.
Right, so the decimal disappears because the nice thing about this PDF is that if we call this guy a, This is minus a, right? So the decimal goes away. Was that your question?
Yep.
Yeah. Any other questions? Okay. Yeah, that's a good question. For a second, I thought there is a mistake also, but yes, it's fine. Okay. All right. So just a few slides of review, right, to sort of like see the big picture where we are. So remember that this is our running example. We have this PDF defined, right, in this region. So it's a joint PDF for X and Y, right? And, you know, we did this basically, we already reviewed the concept of conditional probability, right? So if we want to calculate the conditional probability for Y given X is equal to X, I mentioned that it's incorrect to just plug in X equal to X into the joint PDF, right? What we have to do is that first we have to find the marginal probability of X, right? And then we have to use this equation that tells us f of Y given X is the joint probability divided by the marginal over X, right? And then basically we get a new function, right? So this is our function for f of Y given X, right? And now we can basically integrate that and do whatever we want, right? So if, for example, if we are looking at the current example, right? If we simplify, at the end we get this equation for f of Y given X, right? So if the question wants this, right, then we have to basically find the conditional probability of Y given X, right? And for example, we already looked at this in the previous class. We saw that f of Y given X dy for, let's see, what was the range? So here the PDF is defined, you know, in this range. So Y changes from X to infinity, right? So to check this condition, what I have to do is that I have to plug in here from X to infinity, right? And in fact, if you do this integral at the end, you will get 1, right? So it's correct, right? So this is what we got here. We already looked at this, you know, in the previous class. So this is not a wrong conditional PDF, meaning that it does satisfy this property that if I integrate it over all Y's, it does give me 1. Any questions? Okay. So I basically sort of summarized, you know, a couple of ways that you have to do the double integral depending on your region where the function is defined or where you want to do the double integral. So if your region is a rectangle like this, the order dx and dy doesn't matter, right? So the question is, for example, you know, calculate f of x and y, right? Actually, no, I shouldn't say it like this because now I have to write dx, dy. So I have to write the order now. Basically, the question is calculate probability that x and y are in some region, right? And this is our region here, right? So if our region is a rectangle like this, it doesn't matter if you integrate with respect to x first or with respect to y first. If your region is like this, right? So basically you want to calculate the area under the curve in this region. How should you do the integral? With respect to x first or with respect to y first? So let's see. So if we want to do with respect to y first, y changes from this point, like from this line to here, right? So y changes from, you know, whatever this bound is to this line. But if you are here, then y changes from, you know, this line to this line, right? Or if you're up here, y changes from this line to this, oh, sorry, x, right? Yeah, so sorry. Everything that I said for y, you can switch that to x. So basically x, if you integrate with respect to x first, then depending on where you are, right? If you're down here, your x changes from, so if this is A and this is B, your x changes from, you know, A to this line, right? You have to convert this line to basically y, right? So basically, you have to do your f of x and y dx, right? And then the bound for your x will be from A to this line, but I have to convert this line to y, so x is equal to y minus b1 divided by a1, right? So y minus b1 divided by a1, right? But we see that these bounds are not always the same, because if you're up here, then my x changes actually varies from A to B, right? So because of that, in this case, it's easier actually to integrate from with respect to y first, because my y, if you look at the y, it always changes from this line to this line, right? So in this case, it's easier to integrate with respect to y first. So let me undo all of these, because I don't want these to show up. I have other things to show in this slide. There you go. So basically, we integrate with respect to y first, right? It's easier to integrate with respect to y first, or in other words, to find the marginal f of x, right? When we integrate with respect to y, we get the marginal of x, right? And if your, you know, region is like this, again, the same story, right? It's easier to integrate with respect to y first and find the marginal of x. And what about if your region is like this, a triangle? Is it better to integrate with respect to x first, or to integrate with respect to y first?
Probably x, because then it will always consistently go from that one formula to the other, and then y you have from whatever that height is to the other height at the end.
Yeah, that's correct. So it's easier to integrate with respect to x first, because x always, you know, varies from this line to this line, right? Whereas for y, depending on, you know, where you are, so on this triangle, you have, you know, one bound for y, and in the other triangle, you have another bound for y, right? So because of this, in this region, it's better to integrate with respect to x first, or in other words, to find the marginal of y, right? So that's why I say it's always important to draw your region, right, before you start actually doing the integrals, because the region, you know, will give you an idea of, you know, how to approach the problem with respect to x first or with respect to y first. Any questions? Okay. So similarly, if we want to calculate marginal probabilities, right? If we want to calculate marginal probability of y, we simply integrate with respect to x from this line to the other line, right? From this line to the other line. But if we want to calculate the marginal probability of x, it means that we have to integrate with respect to y, and it means that I have to divide my region into two regions, you know, region 1 and region 2. And at the end, my f of x will have like a form like this. So f of x will be 2 parts, right? So some function in region 1 and some other function in region 2. right? Any questions? Okay. Oops, sorry. So again, here in this case, if I want to calculate the marginal of y, right, marginal probability with respect to y, that means that I have to integrate with respect to x first, and that will not be easy because depending on where I am in region 1, 2, or 3, my bounds change. So in this case, marginal probability of y is again going to have, 3 different parts, right? Part 1 if you're in region 1, part 2 if you're in region 2, and part 3 if you're in region 3, right? But if you want to find the marginal probability of x, then that's easy because y always varies from, this line to this line. Any questions? Okay. All right. So now we introduce the concept of covariance, which is a very important concept, right? So remember we talked about variance before, right? Variance means, how a random variable is allowed, can change in an experiment, right? So remember, when we are rolling a die, for example, right? The fact that we can get a 1 or 2 or 3 or all the way to the 6, it means that we have a relatively large variance, right? The outcome that we get, can change from 1 to 6, right? So covariance is a very similar concept, but it's how 2 random variables change together, right? So let's first define the equation and, calculate covariance, and then we'll actually see intuitively what it means, similar to variance. So before we actually calculate covariance, we need to use this equation, right? So expected value of a function is equal to that function multiplied by the joint probability, summed over, your entire sample space, right? Or if you're in the continuous domain, again, the same equation, but integrated over, your entire sample space. Okay? So let's look at an example how we can use this, right? So basically here, I think we did this example before. Did we? Exactly for the same thing, right? So basically we have, like a cell phone with, 1, 2, or 3 number of bars, and the response time, which is 1, 2, 3, or 4 seconds, right? And the question wants us to calculate expected value of x minus mean of x times y minus mean of y, right? So this is our function, right? So if I go back, or actually I don't need to go back, the equation is here, right? So I want to use basically this equation to calculate this expected value, right? So the h of x that's provided here is h of x and y is x minus mean of x times y minus mean of y, right? So this is h of x and y, right, for this question. Right. So the question wants us to calculate mean of x and also mean of y, and that means that I have to calculate f of x and f of y, right? So to calculate f of x, all I have to do is I have to add up these 4 numbers, right? So if you add up those 4 numbers, you get 0.2. And similar, for the other cases, right? So this means that probability of x equal to 1 is 0.2, probability of x equal to 2 is 0.25, and probability of x equal to 3 is 0.55, right? So always a good idea to do like a sanity check to make sure everything is fine. So if I add up these 3 numbers, what do I get? 1, right? And that should be the case because x can be either 1, 2, or 3, right? So that means that probability of x equal to 1 plus probability of x equal to 2 plus probability of x equal to 3 must be 1. Otherwise, we have made a mistake somewhere, right? And similar for the other, for the other marginal, so for f of y here. So if I add up these three numbers, I will get 0.28, right? And same for the other probabilities. Right? Again, if I add up these four numbers, so it's too sensitive to touch. Okay, so if I add up these four numbers, right, plus this, plus this, plus this, I should get a 1. Otherwise, I have made a mistake somewhere. So now that I have my f of x and f of y, mu of x is easy to compute, right? So mu of x, which is the same thing as expected value of x, right? That's just a notation. That's equal to sigma x times f of x, right? So that means that we did this before, so I will do it quickly here again. So that means 1 times 0.2 plus 2 times 0.25, right? So 1 times 0.2, 2 times 0.25, plus 3 times 0.55. 55. And if you add up these three terms, you will get 2.35, right? So that's your mean of x. Mean of y is computed similarly, and you get 2.49, right? So now that you have these two means, right? You have mean of x and you have mean of y. You simply plug into this equation, right? So this equation now becomes E of x minus 2.35 times y minus 2.49, right? Basically, all I did here is that I plug in for mean of x and mean of y. Right? And now what I have to do, remember expected value of a function is double sum of that function, h of x and y, times f of x and y. Right? What is f of x and y? F of x and y is basically these 12 numbers. Right? These 12 numbers represent f of x and y. Right? So basically all I have to do is that I have to add up, these summation over these 12 terms, right? So let's do some of them. So for x equal to 1 and y equal to 1, so it's 1 minus 2.35, 1 minus 2.49 times the probability, 0.001, right? So we have to repeat these for all of the 12 numbers in this table. And at the end, we get minus 0.5. So the first thing that you can notice is that covariance can be negative, right? And that's absolutely fine. Variance is always positive, but covariance can be negative. So before, I didn't actually mention what this is. So what we just computed, that's the definition of covariance, right? So if you wait a little bit, for a few minutes, we will see intuitively what this number means. Any questions for, the mechanics, how we computed this number? Yeah.
I have two questions. Yeah. So one, you said you were going to explain exactly what that number means, right?
Yeah, later, yeah.
And then the second question, when you were showing the different options, whether it was discrete or continuous, you had dx then dy, but you made a point of saying that we could choose whether we wanted to do dx or dy first. Was that just because you had to write down a notation? Could we choose whether we wanted to do dy or dx, or does it have to be dx, dy?
Yeah, that's a very good question. So the question is here, does the order matter? No, the order doesn't matter. You can swap them, right? But the idea is, depending on the region, right, where you integrate, one of the orders is easier, might be easier.
Thank you.
Yeah, sure. Any other questions? Okay. All right. So what we just did, right, was expected value of x minus mean of x and y minus mean of y, right? And by definition, this expected value is defined as the covariance between x and y. And so this is the definition, right? And it's quite easy to prove that this definition is equal to this equation, right? If you're interested, you can try at home. It's in 1 minute you can prove this. And sigma x and y has units. The units of sigma x and y is the units of x times units of y, right? For example, if x is, the height of students in this class, and y is like the weights, right? And if this is, we measure x in meters and we measure y in kilograms, then basically the unit of sigma x and y is going to be meter kilograms, right? It does have a unit. And sigma x and y can be any number, from minus infinity to plus infinity, right? It can be negative. And we will see what it means when it's negative. Okay. All right. So based on covariance, we define correlation, right? So correlation is defined as covariance of x and y divided by square root of variance of x times variance of y, right? And remember that the variances are positive, and because of that, we can calculate the square root, right? Or if we write that in terms of standard deviation, so this is standard deviation with respect to x, and this is standard deviation with respect to y, right? So remember, sigma x is equal to square root of variance of x. So one nice property of correlation, right, is that it's always between -1 and +1, right? So we call that it's normalized, right? It can't be, outside of -1 to 1 range. And because of that, correlation, is something that we can relate to, right? It has we will see that it has a meaning that we can relate to, right? Covariance is a bit difficult to relate to because it's between minus infinity and infinity, right? But what we did essentially here is that we normalized the covariance. So we divided by the variances of x and y so that we can normalize this covariance. And another nice property of, this correlation is that it's unitless because, so if we go back to the previous example, so if we look at the unit of the correlation, so this guy is going to be meter times kilogram, right? So x is the height of the students and y is the weight of the students, right? And then sigma x is going to have a unit of meter, and then sigma y is also going to have a unit of kilograms, right? So everything cancels out. So rho becomes unitless. And that's another nice property, right? Anything that's unitless, it especially, carries some intuitive information. And if two variables have non-zero correlation, we say that they are correlated. But if the correlation is 0, we say that they are not correlated. Okay. So, before to see what this means, intuitively, let's look at an example, right? So suppose that this is my joint PDF, right? Or more correctly, actually PMF, right? Probability mass function, because this is a discrete case, right? So x can be 0, 1, 2, 3, and y can be the same, 0, 1, 2, 3, right? So these numbers mean probabilities, right? So here, for example, probability of x equal to 0 and y equal to 0 is 0.2, right? So x equal to 0 and y equal to 0 is 0.2, right? So any number that's not given, it means that probability is 0. So for example, probability of x equal to 0 and y equal to 1, for example, right? So if you look here, there's nothing here, right? So zeros are not shown. So this means that it's 0. So any questions about the PMF before we proceed to calculate? So basically what we want to do now, as you probably have guessed, is that we want to calculate the correlation between x and y, right? So what are x and y? For example, x can be like a dose of, some drug that we have given to some patients, right? And y can be the outcome, right? So for example, the doses can be, 0, 1, 2, 3, right? And y can be, like a improvement in the condition of the patient, right? So 0 means no improvement, 1 means a little bit of improvement, and so forth, right? So x and y are two different random variables. Okay, so let's proceed to calculate, first of all, covariance, and then based on covariance, we can easily calculate correlation, right? So remember, in order to calculate, so if we go back, basically this is what we are going to do. We need mean of x and we need mean of y, right? And mean of x and mean of y means that we need the marginal probabilities, right? So I'm going to calculate the marginal probabilities and write them down here. So what is the probability of x equal to 0? I'm going to add up all the probabilities here. So probability of x equal to 0 is 0.2, right? Because there's only one case that x can be 0. Probability of x equal to 1 is the summation of these two guys, and that's also going to be 0.2. Right? Probability of x equal to 2 is going to be the summation of these two guys again, so that's again 0.2. And probability of x equal to 3 is going to be only this guy, so 0.4. So what I wrote here is P of x. P of x equal to, x, or f of x, right? So I wrote f of x down here, right? Similarly, I'm going to calculate, f of y. So again, for this y is going to be 0.2. For y equal to 1 is going to be the summation of these two guys. So that's again 0.2. This guy is again 0.2. And the last guy, which is 3, is going to be 0.4, right? So what I wrote here is f of y. So now based on these, I can calculate mean of x and mean of y, right? That's the first thing I have to do. So for example, let's calculate mean of x. So mean of x is going to be 0 times 0.2 plus 1 times 0.2 plus 2 times 0.2 plus 3 times 0.4. And that's going to be, so this is 0, this is 0.2 plus 0.4 plus 1.2, right? And that's 1.8. Any questions so far? Okay. So always after you calculate mean of x, it's a good idea to, do again a sanity check to make sure it makes sense. So we calculated mean of x and it's here, 1.8. And it does make sense because look at the probabilities. We have 0.2 here, 0.2 here, 0.2 here, but at 3 we have a 0.4, right? So we have a heavier mass, at 0.4. And this 0.4 pulls the mean towards, 3. So that's why the mean is not 1.5 in the middle. The mean is 1.8, right? It's closer to 3. So mean of y, what's going to be mean of y? We don't need to compute it. It's exactly the same thing, right? Because the PDF is exactly the same thing, and it's also changing from 0 to 3. So mean of y is also 1.8. Any questions? Okay. So basically, I did, like the beginning of the computation. So we will see the rest in the slides, right? So here, this picture here shows us, so this picture in the left shows us like a graphic representation of the PDF. I like this one more, right? Because it shows us, visually how the joint PDF looks like. Now I can tabulate those, into this table like this. So for example, this means that if x is 0 and y is 0, probability is 0.2, right? So all of these, how many numbers I have here? 1, 2, 3, 4, 5, 6, right? So all of these 6 numbers are, in these 6 rows of this table. So I calculated the marginals on the slide, right? And these are the marginals for, for x and y. And I calculated the mean, which is 1.8. And, actually, what we didn't calculate is the standard deviation, right? But that's relatively easy to compute. So if I go back here, So I calculated the means. Now, to calculate the variance, for example, variance of x is going to be sigma x squared f of x minus 1.8 to the power 2, right? So this is easy to compute because I have f, right? So it's going to be 0 to the power 2 times 0.2 plus 1 to the power 2 times 0.2 plus 2 to the power 2 times 0.2 plus 3 to the power 2 times 0.4, right? Minus 1.8 to the power 2. Right? So variance is computed quite similarly to the mean. The only difference is that all of these x's have a power of 2, right? So what I wrote in blue is for variance. And then at the end, you have to subtract minus mean of x to the power 2. Okay. Any questions? Okay. So after we compute these, right, whatever the variance is, sigma x is going to be square root of the variance, right? So if I go forward, sigma x is 1.1 and sigma y is same thing, right? Because it's symmetric with respect to x and y. Any questions so far? How we computed the mean and the standard deviations? Okay, very good. So now I want to calculate the covariance, and remember the definition of the covariance of x and y was expected value of x minus mean of x times y minus mean of y, right? Which is equal to sigma of x minus mean of x, y minus mean of y, and then f of x and y, right? So what I have to do is I have to compute x minus mean of x and y minus mean of y. right? So for x equal to 0 and y equal to 0, x minus mean of x is going to be minus 1.8 because mean of x we calculate, oh, actually it's here, it's 1.8 and 1.8. So, and then I compute the product of these two guys, right? So 1.8 times 1.8 times 0.2, right? So this number here, product column, oops, sorry. So product column at the end, this number represents x minus mean of x times y minus mean of y times f of x and y, right? So 1.8 times 1.8 times 0.2 is going to give me 0.65. Any questions? Okay, and so basically now I computed one term of this equation, right? So this guy here is this guy here, right? So I computed one term of this equation. All I have to do is I should compute all of the terms of this equation, right? So, and then I add them up. So the number that I get is the covariance. (1.2). And to compute the correlation is covariance divided by sigma x times sigma y, right? So you basically normalize it. And then our correlation is going to be 0.92. So as you can see, it's, you know, you have to practice a few times, but there's nothing, you know, conceptually difficult here, right? You follow certain steps, right? So again, in my opinion, this chapter, like everything in this chapter, is much easier than chapters 2 and 3, where, you know, questions can be quite tricky. You have to figure out, oh, what is this distribution, right? I think that's much more difficult than these. But, you know, of course, it's important that you know the steps, right? Once you know the steps, it's always follow the same steps. Any questions? Okay, so now we can actually intuitively look at what these numbers mean, right? So correlation of 0.9, remember the maximum amount that correlation can take is 1, right? So 0.9 is a large correlation. It's considered a very large correlation, right? And if we look at our joint PDF here, you know, in this plot, generally what happens is that when x increases, y also increases, right? So for example, if we go back, you know, at the hypothetical example that I said, like x is the different doses of the drug that you're giving and y is like the improvement that you see. We see that as we give more and more doses, right, y generally increases, right? So we say that x and y have a large correlation. This correlation is 0.9, okay? Because generally when x increases, y increases. Right? So if we look at the weight and height of the students in this class, you know, I'm sure correlation would be large again. Because usually if somebody's taller, you know, that person is also heavier. Right? So it means that if x is height and y is weight, again, x and y are highly correlated. So when correlation is 0, something like this happens. So if this is x and this is y, as we increase x, you know, nothing happens to y, right? Sometimes it goes up, sometimes it goes down, right? So there's no trend in the data. So look here in this plot that we have, you know, we see that the trend is clearly upward, right? So in this case, correlation is 0, right? And when is correlation negative? Can anybody think of an example where like correlation is negative? Let's say negative 0.5 or negative 1. Yeah?
So when the points are below the line, below the x-axis, like all the points?
You mean something like this? No, this is still zero correlation because as x increases, nothing happens to y.
Actually, it's the points are downwards.
Yes, exactly. Yeah, that's what you meant. Yeah, you're right. So the points go downwards, right? So as x increases, y goes downwards, right? So you see here, like this line that I drew here, the slope is positive, and that means correlation is positive, right? If the slope was negative, then correlation is negative, yeah. Okay, any questions? So basically to give you like an intuition into what is covariance, I can't do that, but instead I can give you an intuition into what is correlation, right? And correlation and covariance are very closely related, right? They are essentially the same thing. Correlation is normalized version of the covariance, right? So it helps us, better understand covariance. Any questions? Okay. So we talked about correlation, right? And correlated and uncorrelated random variables. And, today and many times before, we had talked about independence, right? These are two different things. They don't mean the same thing, right? So if x and y are independent random variables, then covariance and correlation, both of them are zero, right? So if two events are independent from each other, then the correlation between those two events is zero, right? But the other way around is not correct, right? You can find random variables that have a zero correlation and zero covariance, obviously, but they are, not independent. They are dependent on each other. Right? So independence, in fact, is a stronger condition than zero correlation. Right? So this part is, in fact, the first part is quite easy to prove, right? In fact, I encourage you to prove it at home, right? So remember that independence means that f of x and y is equal to f of x times f of y, right? This is independence. So from this, you can prove that expected value of xy is equal to expected value of x times expected value of y, right? And therefore, from this, you can say that the covariance of x and y is zero, right? But unfortunately, we can't go these steps in reverse. The reverse doesn't hold, right? So that means that if covariance is zero, we can't prove that the two random numbers are independent. Right? So this part, the second part, is beyond the scope of this course. We don't talk about it in this course, but I can show you some examples, right? So the numbers that you see up here is the correlation between x and y. So this axis is x, and this axis is y. And the numbers that you see up there are correlations. So for example, in this case, the correlation between x and y is -1 because this is a perfect line in -1 direction, right? Here, the data becomes a bit noisy. There is generally a trend in this direction, but, you can move, randomly in different directions as well. Because of that, correlation is -0.8, right? And in this case, in the middle case, there's no correlation. So, x and y change randomly, right? So in this case, in fact, is a case where x and y are independent from each other. So in this case, they are independent. Okay? So basically the third row of this graph shows us many examples where the correlation is zero, right? So this is correlation. So correlation between x and y is zero, but so this is y and this is x. The correlations are zero, but x and y are dependent on each other. Right? So if you're interested, you can basically read this PDF. It's a very nice PDF that basically shows, what types of distributions, have this property that are not correlated, but they are dependent on each other. Any questions? Okay. Right. So, like one of the reasons that I say this course is important, not just because you guys are engineers, but in general in your life, right? Because, this course gives you the tools to, understand BS, right? So there is, a lot of arguments are not sound. And, in fact, you often find even papers, scientific papers that, make incorrect arguments, right? So this course actually gives you tools to, understand, those incorrect arguments in general in life, So here, there was so I mentioned the website down here, right? So I got this from a website, right? So if you look at things randomly, right? If you look at, there are many, events. For example, like in this case, in the top graph, the x-axis shows bedsheet tangling, right? And the y-axis shows cheese consumption, right? So, like you look at random things, for example, color of shoes of the people, or, size of the bed, or, you look at many, many different things, right? And then if you look at, all of the combinations of those different things, by chance you can find a correlation, right? So in this case, you can see, the x-axis is the year, the black curve is bedsheet tangling, and the white and the red curve is cheese consumption, right? So you can see that there is a very strong correlation between, the black and the red curves, right? But, there is no causal effect that connects these two together, right? So this correlation is probably just by chance, And that's why I recommended you guys to watch that Vsauce video that looks at coincidences, right? So not every correlation means, oh, there was actually something going on. Some correlations are just by chance, right? Or the other curve down here, the x-axis shows the number of pirates, right? And the y-axis shows global average temperature, right? So this curve, clearly shows that there's a strong correlation between number of pilots and global temperature. But it doesn't mean that, if we have more pirates, so to combat global warming, we have to reduce the pirates, right? So, it could be that some other factor contributed to both of these, so there was some factor, like, for example, higher population, right? If you have higher population, by chance you can have higher pirates as well, right? And more population also probably leads to more global warming, right? So remember, correlation is not a causal thing, right? So it doesn't mean one of them caused the other thing, right? Or this other example that I really like. So this is actually I checked this. This is not fake news. This is actually from Fox News, right? So they actually showed these basically statistics where they showed that, when black men are assassinated, the stock market goes up, right? So like here you can see George Floyd, Michael Brown, Rooney King, and MLK, right? And in every year, I didn't watch, I don't watch Fox News, but, I don't know what was the argument, right? But, if you have only 3 data points, right? So actually, sorry, in this case, 4 data points, right? You can show correlations just by chance, right? Because you don't have enough data to, to substantiate your claim that, oh, these two are correlated with each other. Okay. All right, so let's try to do an example, right? So here we have a joint PDF, right? PDF here is simpler than the other PDFs that we saw before. It's just x times y. And the region is also an easy region. It's between 0 to 2, and y is between 0 to 4, right? So what I want to do is I want to calculate the covariance of x and y. Okay, so let's try to do this. Okay. Okay, so let's write down the PDF xy divided by 16, right? F of x and y is xy divided by 16 and is defined in this region. 0 to 2 and 0 to 4, right? So this is 2 and this is 4. X and y, right? So I want to calculate the covariance between x and y, right? So, covariance, like the conditional probability, the first thing we have to do is we have to find the marginal PDF, right? So f of x is going to be integral of f of x and y dy, right? So if I look at the curve, y changes from 0 to 4. Oops. 0 to 4, right? So this is going to be x divided by 16 times integral of y dy from 0 to 4, right? And that is x divided by 16 times y squared divided by 2 from 0 to 4. Oh, so this is x, right? And this one is multiply, right? So maybe I just showed this as this. This one is multiply. So that is going to be x divided by 16 times, and y is 4 squared is 16, right? Times 8, and that's x divided by 2. Okay. So that's my f of x. Hopefully we didn't make a mistake. Yeah, it looks okay. Any questions so far? Okay. And now f of y is going to be integral from 0 to 2 xy divided by 16 d of x. And this is going to be y divided by 16 times x squared divided by 2 from 0 to 2, and that's 4 divided by 2, that's 2, and that is y divided by 8, right? Any questions so far? Okay, so now, so now actually when I look, I see that f of x times f of y is x divided by 2 times y. That's xy divided by 16, right? And that's equal to f of x and y. Right? So since this equality holds, right? So since this equality holds, then I can say that x and y are independent. right? And since they are independent, then because of this, I can say that the covariance is 0. Any questions? So here in the slide, the solution is a bit different. This is also correct, right? So here in the slide, so actually I don't like this style because E of x is calculated in one shot directly from the joint PDF. And I don't think that's a good idea. It makes it very prone to making mistakes, right? So what I like instead is that first you calculate f of x as we did here, right? And then from this f of x, so done. And now we can calculate E of x based on this, right? So we can say based on this, E of x is sigma x f of x. So x times x divided by 2. Oh, sorry, not sigma, integral, right? So integral x f of x from x d of x, right? And x varies from 0 to 2. So that's going to be integral of x squared divided by 2 from 0 to 2. And that's going to be x to the power 3 divided by 6 from 0 to 2. And that's going to be 8 divided by 6 or 4 divided by 3, right? So I actually calculated E of x in 2 shots instead of directly. First, I calculated f of x, and then I used this equation to calculate E of x, right? And I really recommend you to, to calculate it in 2 shots, because in 1 shot, it's really more difficult, in my opinion. So let's just check if we didn't make a mistake. So E of x is 4 divided by 3. If I go back, yes, it's 4 divided by 3. Okay. And similarly, we can calculate E of y and E of xy. And if we plug in, we see that they are 0. Right? But we didn't need to do all of these. As I showed in the previous slide, once we calculate f of x and f of y, we clearly see that the multiplication of these two is equal to the joint. That means that they are independent. That means that that's 0. So we don't really need to calculate E of x or E of y or E of xy. Okay? Any questions? Okay.